Well, thanks everyone for joining this talk, this stream. I know you guys had a couple of other really great options, and it's also Friday at the end of the week, so I appreciate everyone taking time to sit on a Zoom meeting for an hour and listen to me talk to my computer. So my name is Madeline Magee, and I'm currently at the Wisconsin DNR in our Office of Great Waters. I've been here for about 2 years, but before I came to DNR, I worked at UW-Madison on climate change impacts to lakes in Wisconsin, which is what I'm going to talk about today. So, like I said, talking about climate change impacts to Wisconsin lakes, I'm going to start with just a little bit of kind of information about climate change in general and climate change in Wisconsin to kind of set the stage. Then talk about some impacts that we have already observed in Wisconsin lakes and that we kind of expect to see moving forward. And then end with some discussion on climate adaptation strategies.
Right,
And
Madeline.
at any, oh, go ahead.
Oh, sorry, I was just going to say quick for the participants on Madeline's talk today, if you're just joining us right now and you're not quite familiar with Zoom, I just wanted to let you know for questions, if you kind of scroll on the bottom, you'll see that little chat function and enter your questions in there, and I'm going to help moderate those back to Madeline. So that's how we'll deal with the questions. And
Great.
then Madeline, you just kind of want to go with the flow with questions as we go.
Yeah, so if anyone has especially any clarifying questions while I'm talking, feel free to put them in the chat and Lisa will go ahead and ask me. If it's a maybe a longer question, maybe hold those just to the end so we don't get off track on time too much, but I've tried to leave quite a bit of time for questions. So if you have any questions, feel free to go ahead and throw them at me and I'll do my best to answer them.
Okay, thank you.
Yep, thank you. So I guess we'll move on to the next slide. Thanks. So global temperature is increasing. I guess we'll just start right off with how things are in terms of climate change. And I don't want to kind of go into a lot of the details about climate change and why some areas experience different changes versus other areas. I'm going to try to keep it general with kind of the big picture take-home messages for both globally and then Wisconsin specifically. But the big piece of information that we have right now is that global air temperature has warmed by about 1.5 degrees Fahrenheit since the early 1900s. So this graph here on the left shows the kind of global land and ocean temperature anomalies since about 1880. So anomaly is kind of a weird term. It might be easier if they just showed what the temperature was, right? So what they do, that 0 bar is kind of considered the average over this time period, 1880 to nearly 2020. I think the graph goes until about 2017 or 2018. And blue bars are years that have temperatures kind of lower than what was that long-term average. Red bars are years with temperatures above that long-term average. And as you can see, since I don't know if you guys can actually see my arrow or not, so I'll try to speak and show my arrow at the same time. But since about the late 70s, every single year has been over the kind of mean temperature over the time period. Thanks. I think Pat's moving his arrow, so thanks, Pat. If we look kind of towards the right side of the plot, we see that, with each year that change above kind of that long-term average has gone up, and the last few years, so the last 3 years on this plot are actually the 3 warmest years, and that is a trend that we've seen consistently the last couple of years. 2015, 16, 17, 18, and then I think 19 as well, all broke records for being kind of the warmest year. that we've seen globally. So next slide. In Wisconsin, our air temperature is also increasing, kind of unsurprising, although there are kind of small spatial variations across the state. So looking at the left figure, this larger one, this shows the historical change in annual mean temperature from 1950 to 2016. So since that time, we've seen, depending on the part of the state you're in, a 2 to 3 degree Fahrenheit increase from the 50s until 2016. So that change has actually been higher. Many of you are in the northern part of our state. So that change has actually been higher than some locations in the southern part of our state. The two plots kind of on the right side of the screen here in red actually show the seasonal changes across the state. And the units here are a little bit different. The units here are in degrees Celsius instead of degrees Fahrenheit. So I'm sorry for the different unit change here. But I want to show these plots to show that while our mean average temperature has gone up, if we look seasonally, most of the change, most of the warming has been in winter and spring. And you can see that there's a pretty clear kind of spatial variability across the state for both seasons, with excuse me, most of the warming kind of happening in the northwest portion of our state, whereas in the northeast, far northeast portion of the state, temperatures have actually maybe seen a slight decrease in winter and spring temperatures over the last 60, 70 years or so. So next slide. In addition to warming air temperatures, which I think most people are kind of pretty familiar with, Wisconsin has also seen more extreme rainfall. So this extreme rainfall is true globally. An easy way to think about it on a global scale is if you live in an area that is normally fairly dry, those areas have gotten drier. In areas that are normally maybe a little bit wetter, those areas have gotten wetter. In Wisconsin specifically, we've seen a pretty large spatial variability across the state. The southern part of the state from about the 50s to the early 2000s got wetter. So our annual average precipitation kind of in the southern part of the state has increased, depending on location, by as much as 7 inches. So 7 inches of rain increase between 1950 and 2006 every year. In the northern part of our state, though, we've actually generally seen the opposite, with actually decreases in annual average precipitation. And that decrease in the northern part of our state has been up to about 4 inches. So a lot of spatial variability here. On the right plot, I'm showing the increase in days per decade with 2-inch rainfall. So a 2-inch rain event in kind of one day is by the climatologist seen as kind of an extreme value. And so we see a similar pattern in the southern part of our state. We have more days of these large rain events, and in the northern part of our state, we've seen fewer days with these large rainfall events. So next slide. So that's what we've seen over the last, 50 or 60 years. But what may be a more important question for some of us is, what can we expect? And that answer is, we feel pretty confident, kind of the direction of that answer for air temperature, although there is kind of some uncertainty around the exact change that we expect. So generally, we expect our increasing air temperatures to continue. This large plot on the left shows our projected change in annual mean air temperature from 1980 to 2055. And for most of the state, we're projecting about a 6 degree Fahrenheit increase in air temperature by around the year 2055. But like I said, there's some variability around that. So this plot on the right kind of illustrates that a little bit. The way we do these projections, because a lot of variables can impact, what we may see both through time, kind of an average, but also in any particular year. So what the climate modelers do is they have different climate models that start with different initial conditions that kind of process or estimate known physical processes differently, kind of in the computer space. And also we have different expectations for, how much CO2 is going to be in the atmosphere. What changes might people make at a local level that could alter, the impact of climate change? What mitigation processes might be taking place? That kind of thing. So the sum of all these models shows that we are expected to warm realistically anywhere between 3 and 9 degrees Fahrenheit by the mid 20th century. So we feel, very confident with about 95% certainty that in 2055, when we look back, we'll say, yep, it's somewhere between 3 and 9 degrees warmer than it was in about the year 1980. And kind of the mean of all those models is around 6 degrees Fahrenheit. So next slide. Precipitation, however, is a little bit more complicated. So like I said, we feel very, very confident that air temperatures are going to continue to increase. But precipitation is both a lot harder to model, so it leads to more uncertainties, and there are a lot more variables that play a role, which increase the uncertainty. So what I'm showing here are our projected precipitation increases for winter. So winter would be December, January, February, and spring. Spring is March, April, May. Across the state for both of these seasons, regardless of what climate model we're using and kind of what conditions we put into that model, they all show that we can expect increased precipitation during the winter and spring. For the spring, this precipitation will, of course, fall in the form of kind of rain, most likely. In the winter, this means we will have both increased snowfall, but also increased winter rain events. So while we will have increased precipitation, that doesn't necessarily mean we will have increased kind of snow across the landscape or anything like that, because the exact temperatures at the time of precipitation are going to make a big impact. So this is what we feel very confident about. We're going to have increased precipitation during the winter and spring. We feel less confident about what will happen in summer and fall. Some of our climate models show that there will be increases in precipitation. Some climate models show that there will be decreases in precipitation for both seasons. When we look at kind of the average of all the models, we're left with no net change, but we don't really have a best guess as to what will probably happen moving into the future. So next slide. So that's kind of the climate side of the story, what we know and what we feel confident about. But you guys all care about lakes, so you probably just really want to know what this means for lakes. Maybe lakes in general across the state, or maybe you live on a lake, you have a cabin on a lake, maybe there's just a particular lake that you really care about. So what does this mean for our lakes? For this section, I am going to focus on things that we feel very confident about, both on our understanding of climate change, our understanding of physical, chemical, biological mechanisms in lakes, and what we have good evidence for. This is not going to be an exhaustive list of every possible change that could happen. I'm going to focus on ones that are pretty consistent across a variety of lakes. And also for this section, focusing on topics that I actually know really well. So my research background is in lake physics, lake water quality, and fish habitat. So those are kind of the three topics that I'm going to cover. Climate changes will also impact a variety of other portions of the lake ecosystem. but personally know slightly less about those, and also some of those other areas aren't quite as clear. They're slightly more lake dependent. So next slide. So first, ice cover. Across the state of Wisconsin, over the last 100 years or so, based on all the evidence we have seen a decrease in ice cover duration across the state. So this particular plot shows ice cover duration for Lake Mendota, which is in southern Wisconsin. It's in Madison. And over the last 150 years or so, Lake Mendota has seen about a month less ice cover than it did historically. So this year, next year on average, we're seeing, a full month fewer ice days than we did, in the late 1800s. And this is true for almost all of our lakes across the state. Not necessarily a full month, depending on location, but in general, lakes across the state have seen significant decreases in the period that they have ice on them. Next slide. So moving into the future, we expect this change to continue. And as you kind of, think back to that pretty steady decreasing trend, eventually that's going to lead to lakes with no ice cover if lakes continue to, or if air temperatures continue to warm as they have. So this plot is actually from a global study that myself and some other colleagues from across the world, but quite a few in Wisconsin, worked on. And globally and also in Wisconsin, like I said, we're going to experience fewer lakes with ice cover. So you can see as this kind of scrolls through, all of the orange dots here are lakes that don't have ice cover every single year or every single winter. All of that kind of like light bluish grayish color, those are all lakes that have ice cover every year. So starting in October or November, the lake forms ice and it keeps ice cover, until the spring when it melts. You guys are all kind of familiar with this process. And what we see here, if you kind of look towards where Lake Michigan is in North America, that can kind of give you an idea of what we expect for Wisconsin, that even under, a fairly small air temperature change of 2 degrees Celsius, 2 degrees Celsius is kind of the goal of the Paris Climate Accord. For those of you who are familiar with that, what we actually see is that a significant number of lakes in Wisconsin are projected to no longer have ice cover every year. That doesn't mean that they won't have ice cover in every single year. What'll start to happen is maybe one year the lake won't freeze. Then maybe it'll freeze for 2 or 3 years. Then 2 years in a row it won't freeze. And the number of years that the lake doesn't freeze will increase as our air temperatures increase. And you can see once we get to like 3.5 degrees Celsius, most of the lakes in Wisconsin will not consistently freeze each year. Next slide. So in addition to lakes sometimes not freezing, which isn't great for Wisconsin lakes anyway, when lakes do freeze, we expect them to have thinner ice cover. So this plot here shows results, ice thickness results from a modeling study for a few lakes in Wisconsin. So the x-axis is just kind of the year of the model. The y-axis for each one of these lakes shows the air temperature change from our historic average. So 0 is kind of current conditions. We looked at lakes getting colder and then lakes getting warmer as well. The colors show the ice thickness. So that kind of very light blue color means thin ice. The very dark blue color means thicker ice. If it's black, that means in our model the lake didn't freeze at all, so 0. And what we see is that once we start to increase air temperatures with temperature increases, fairly small 3 to 4 degrees, we start to see significant thinning of ice cover. So normally most of these lakes have 60 centimeters or more of ice cover in any given year. But even when we start to get to, a 2-degree temperature increase, 3, 4-degree temperature increase, even when there is ice cover, that decreases significantly to only 10 or 20 centimeters. So as you can imagine, this can pose, a health and safety risk for folks that are out on lakes. People are used to, in January and February when there's ice on a lake, especially in northern Wisconsin, that you can go walk out onto the lake to go ice fishing. You can ride your snowmobile on the lake. You can put your truck out on the lake. So this is kind of the situation that people have, we have in our minds, but you saw we're expecting up to, 6, maybe even 9-degree temperature increases by the mid-century. So that will result in significantly thinner ice cover. And it may not be safe for folks to go out on the lake and go ice fishing in January or February. Definitely probably shouldn't be taking your truck out on the lake. So this can cause a couple of problems and something that, we're really interested in from kind of a safety standpoint. Next slide. So I'm going to move next to talking about water temperatures. As I think a lot of you can probably guess, if air temperatures are warmer, probably the water is going to be warmer too, and that's true. So this plot is work from Gretchen Hansen and some other folks in Wisconsin, Minnesota, and Michigan, looking at surface lake temperatures. The kind of left portion of this graph shows temperatures from kind of the historic period, so the 80s through 2015, 2016 or so. And each color here represents the average lake surface temperature for a distinct ecoregion that corresponds with the colors on the plot up there. And in, the kind of northern areas of Wisconsin are kind of the salmon color and that light green color. Depending on where you are, most lakes are maybe 21 to 23 degrees Celsius right now. But if we look at climate projections and put them on top of lake models, what we see is that we can expect a significant increase in air temperatures by both the mid-century, so that kind of 2040 to 2060 highlighted portion, and then also the end of the century, so the 2080 to 2100 portion. And in northern Wisconsin, if we kind of look at those light salmon and light green colors, by the mid-century, our surface water temperatures are probably going to be from around 23 degrees Celsius to maybe even as high as 25 or 26 degrees Celsius. So our cooler lakes will be the same temperature as our warmer lakes are now. When we look towards the end of the century, we see even more increase in temperature by the end of the century. Our coolest lakes may be 26 degrees Celsius and our warmest may be as high as 28 degrees Celsius. So significant impacts to surface water temperatures. And I'm going to get to this a little later, but as you can imagine, if we have changes in ice cover and changes in temperature, that's probably going to somehow impact our biological components of the lake. So our fish, the animals that live in the lake, things like that. So next slide. So now I'm going to move on to talking about water quality, but in this case specifically algal blooms. Over the last 30 years or so, we have seen an increase in algal blooms, both kind of regionally and in Wisconsin, and then increase in chlorophyll, increase in kind of, or a decrease, excuse me, in water clarity, so measured by kind of like a Secchi disc, figuring that. And we've seen this has been pretty consistent, generally speaking, although each lake doesn't necessarily respond the same. So these kind of blue colors on this plot here, this is from work by Sam Oliver at UW-Madison. The blue colors are lakes that have seen a decrease in chlorophyll A concentrations. The red colors are those that have seen an increase. So even in Wisconsin, you know, there's a couple lakes that have seen a decrease in chlorophyll A, so a decrease in algal blooms and lake productivity, but most lakes that have been changing have actually seen an increase. And this isn't all completely due to climate change, of course. We have land use changes at the same time, but climate does play a big role in algal bloom and algal production because, as I talked about earlier, we have seen increased precipitation events. And as you have larger rain events coming down on your landscape, you can get more nutrients coming into your lake. I think a lot of you are probably familiar with this process. But this is what we've seen is happening and also what we expect to continue happening in the future. So next slide. Yep, so the idea or what we expect to happen is because we have these large rain events, we have more rain falling on the landscape and therefore more runoff going into our lakes. And as I think a lot of you are probably familiar, if we have more rain, we have more runoff, that means we have more nutrients, more sediment coming into our lakes as well. So this increased nutrients can result in increased algal production. So larger algal blooms, more frequent algal blooms. One of the reasons that we expect this to continue is that, as I said before, all of our best kind of climate projections are showing increased precipitation in the spring. The spring is actually when we get the largest load of nutrients into our lakes. So while we may have decreased precipitation under some of the models in the summer and the fall, because every model across the board is showing increased precipitation and increased extreme precipitation in the spring, we feel very confident that we will have more runoff entering our lakes and therefore more nutrients coming into our lakes. So next slide. Thanks. So the next thing that I'm going to talk about here are fish and fish habitat. So I'm going to first talk about cold water fish. And there's kind of two figures shown here. I'm going to talk about the one on the left first. And this left figure shows what's called the measure of available habitat. This is for one particular lake in Wisconsin, but the kind of direction of change here is true for all of our cold water lakes in Wisconsin. I'm not going to go into detail about the metric itself, but what you need to know is that low numbers on this graph are good. So the low numbers show good habitat and the high numbers show bad habitat. And looking across the state, what we've seen is that over the last 30, 40 years or so, when we measure this cold water fish habitat, which takes into account both the water temperature and dissolved oxygen availability, we see that habitat is decreasing within lakes across the state. And this decrease is driven by two climate factors. So if you look at the graph over here on the right, this is kind of a color plot that shows the response of habitat to air temperature and phosphorus changes. So I'm showing air temperature and phosphorus here because we did a pretty extensive modeling study and showed that these were the two main drivers for poor cold water habitat in Wisconsin. So again, you don't need to know kind of the details of the numbers itself, but low numbers are good, high numbers are bad in this color plot, and the kind of blue color is good habitat, so those are lower habitat metrics, and the kind of yellow golden color is bad. And when we did this modeling exercise, what we found was that as we increase air temperature, we also increase water temperature, which leads to less habitat for cold water fish. At the same time, as I just talked about on the last slide, we're expecting increased phosphorus loads because of increased precipitation. These increased loadings will result in more algal blooms. As we have more algal blooms, that means we have more organic material that can be decomposing kind of at the bottom of the lake. And as that material decomposes, the bacteria that actually do that decomposition use up oxygen. So if you think about being a fish, a cold water fish specifically, which needs cold water and lots of oxygen, that fish basically is getting pinched out. The area that it can live is getting pinched out because there's less area in the lake with enough oxygen, while at the same time there's more area in the lake that has temperatures that are too warm, or less area that has temperatures that are cold enough for the fish. So these two changes, these two climate changes basically act to kind of enhance each other. So if we just look at air temperature by itself, assume no change in rainfall or no change in phosphorus load, we move from kind of good cold water habitat to not as good cold water habitat. We're kind of in this green color if you look at the bottom of this square plot. But if we have our air temperature change while at the same time having increased rainfall events, and then increased phosphorus loading, we move from not great habitat up to really bad habitat. So these two changes kind of act on top of each other for reducing cold water fish habitat. Next slide. And we actually see this play out in cold water fish abundance. So the left plot is for lakes across the Midwest region, not specific to Wisconsin. But if we look at one cold water fish in particular, Cisco, what we see is that since the kind of early to mid 70s, there's been a decrease, a pretty significant decrease in the number of fish in lakes that support cold water fish. If we look at the plot on the right, this shows in Wisconsin kind of what our Cisco populations look like in lakes that have Cisco across the state. So in the kind of early 2010s, Wisconsin DNR repeated a survey of kind of historic Cisco lakes across the state. And what they found was most of the lakes that have Cisco in our lake have low or only moderate populations of Cisco. We have far fewer lakes that have what would be considered very high or high populations of Cisco. And this isn't special to just Wisconsin. Like I said, other states in the Midwest have been seeing the same thing. So Michigan and Minnesota in particular, kind of provinces in Canada have seen the same thing as well. They've seen decreases in lakes that support cold water fish, and also decreases in populations of cold water fish in their states. So next slide. In addition to kind of an impact on cold water fish, we have also seen a transition from lakes that support cool water or cold water fish to becoming lakes that have more warm water fish species. So this graph shows a plot from Gretchen Hansen and some other folks in Wisconsin who were trying to correlate who were trying to investigate the change in walleye reproduction or walleye recruitment in lakes in Wisconsin and largemouth bass populations. And so what they found was the biggest indicator of whether a lake can support natural walleye recruitment or whether it will be more supportive of a largemouth bass population is actually what they are calling degree days. So I won't get into too much detail there, but degree day is basically a cumulative summation of how warm the lake is throughout the year. So the left are lakes that are cooler, and these lakes, they have a lower degree day because the water temperature doesn't get as warm. Lakes on the right side are warmer. And then the y-axis shows kind of the probability of, in this blue color, walleye recruitment, and then in that salmony color, largemouth bass. And so we see as we move from lakes that have a lower number of degree days, so lakes that are generally cooler, those lakes have higher probability of walleye recruitment and lower probability of largemouth bass. As we transition to warmer lakes, we kind of see a pretty significant decrease in natural walleye recruitment, and then a sharp increase in largemouth bass populations. So this is consistent across the state. Other states have seen the same thing. And moving forward, we expect this transition to essentially continue. So lakes that maybe are still cooler now, we're expecting them to warm up. And many lakes across our state are going to transition from maybe being lakes that are good for walleye and other cool water fish species to lakes that are better for warm water fish species such as largemouth bass. So next slide. Great, so that's kind of an overview of changes that we expect or that we have seen and what we expect in the future, which is great. It's very important to know about, but I think at least what I care about and what maybe some of you might care about is, well, what can we do about those changes? How can we kind of reduce the impact of climate change on our lakes in Wisconsin? So next slide. So to answer this question, a couple of years ago now, we pulled together a large group of people in Wisconsin from the DNR, from all of the UW system schools, from federal agencies like USGS, from local county conservation agencies, local resource managers, into a workshop to essentially develop a list of what we could do, what climate change adaptations could we take on a lake level to reduce the impacts of climate change. And our workshop focused around kind of 4 specific areas. So the first was lake levels. Now, I didn't talk about this earlier, but I'm sure many of you, whatever lake you live on, the lake level hasn't been consistent during the time that you have been on it. And some lakes in Wisconsin have seen increased lake levels. Some lakes in Wisconsin have seen significant decreases in lake levels. So we also focused on water quality, which I've already talked about a little bit, fisheries, which I also talked about a little bit, and then also aquatic invasive species. Now, I didn't focus on this in kind of the coverage of what will happen to lakes in Wisconsin, because the real answer is we know that every lake in Wisconsin is going to be more susceptible to invasive species, but we don't know which lake will be more or less susceptible to any particular species. A lot of that is going to be very lake dependent, both because of the changes that are seen at the specific lake, but also because of transport mechanisms of AIS species as they move from lake to lake. So the main story for AIS is that we know we're going to have more invasive species, but we don't know which ones in which lakes, or at least we don't have a very clear idea of which ones in which lakes. So most of our adaptation strategies, spoiler alert, will need to focus on just keeping AIS out of our lakes in general. So next slide. So like I said, we had a workshop where we kind of brainstormed different adaptation strategies based on these 4 themes and different approaches. What we found from all of our kind of practitioners and knowledgeable experts was that all of our climate change, adaptation strategies need to, of course, focus on how the lake is going to change. So, what is the mechanism of change and how do we stop that? At the same time, we also need to consider the human dimension. So what can we reasonably accomplish? There are social factors, political factors, economic factors that will all impact which adaptation strategies may work on a particular lake, and then also how effective they may be or how likely they are to be implemented. So next. So within this framework, considering the overlap of the ecosystem and the human dimension, our adaptation approaches fit into 3 categories: resistance, resilience, and response. So I'm going to talk about each one of these kind of in turn. Next slide. So with these three R's, the first is resistance. I'm going to use examples all dealing with water quality, just to kind of be consistent and help kind of explain the difference in these three strategies. But we do have strategies for, all four of those thematic areas. So the first strategy that we have are tons of strategies related to resistance. And the idea here is that resistant strategies defend our high value lakes against changes caused by climate. They identify, an exact mechanism of a negative change and they remove it. So one good example of this is eliminating or reducing combined sewer overflows. Many municipalities in our state have combined overflows where during large rain events, sanitary and storm waste are being mixed and they're both discharging into our rivers, which may lead to lakes or directly into a lake itself. Removing these overflows actually basically physically removes the mechanism that would cause a negative water quality impact from climate change. So next slide. The second of our R's is resilience. The idea here is that we can reduce stress and minimize vulnerabilities, either through actions on the landscape, through policy, etc. One example of this is wetland protection and restoration. As I'm sure everyone listening here knows, that wetlands are really great for lake water quality. They are able to filter out nutrients before it gets to the lake. They're able to slow the flow of water and kind of the pulse of flood during rain events, so we don't have kind of high changes in lake levels or large sediment loads that would come into the lake that would negatively impact our lakes. And we're not, preventing rain from going into our lake. We're not kind of removing that, but we're putting a system in place either by protecting wetlands or doing wetland restorations so that the stress is reduced and our lakes can be less vulnerable to large precipitation events. Next slide. And the last of these R's is response. So the idea here is that, there's going to be changes that we can't really do anything about. Maybe we don't have a mechanism for reducing the impact, but what we can do is we can find ways to accommodate the change, but minimize kind of undesirable outcomes as much as possible. So this example here shows what are called water exposure treatment systems. And many people in the state who maybe don't necessarily live on a lake, but they access water through public beaches. And we know in some areas, either due to characteristics of the watershed or kind of social and economical factors, we may not be able to completely remove algal blooms. But what we can do is what they've done here at this beach, which is basically develop an in-situ swimming pool. So if you look at the picture, you can see inside this kind of barrier, the water is clear. You can see to the bottom. Outside the barrier, you can see that we do have a large algal bloom. So this protects the use and the ability of people to kind of recreate in some locations of our lake, even though perhaps we don't have a way to completely remove the negative impact of climate change. So next slide. So within these kind of 3R approaches, we have specific adaptation actions that fall into 4 different very important categories. And I'm again going to kind of go through them, and I apologize because it's going to be a lot of words. So next slide. So the first kind of category of adaptation action is communication. So it's really important to communicate what exactly climate change impacts are going to be to the various stakeholders so that we can develop adaptation strategies, communicate both the positive and negative impacts of proposed strategies, and manage expectations for results and for resource use in the future. We can't figure out, what the best way to protect our lakes is without having everyone on the same page about what the impacts are going to be. Next one. So the next category are policy changes. So rules and regulations that can promote kind of these 3 Rs on a structural level. Next slide. So the third are conservation approaches. Many of kind of our traditional conservation approaches across the landscape will have positive impacts from a climate adaptation standpoint. So we know that, wetland protection and restoration is a traditional conservation practice, and it is going to have added climate adaptation benefits. Next slide. And then finally, a set of actions falling in the engineering category. So we will continue to need new and innovative technologies that can respond to climate changes, that can help reduce negative impacts to the lake resource. While our conservation and policy and communication changes, our adaptation strategies, are all important, we do need to continue to look to new and innovative technologies. Next slide. So I'm just going to show an example here for lake levels of specific adaptation strategies that fall into these 4 categories. So we have communication strategies that also include, monitoring, figuring out what range of lake levels we expect, and then communicating that with the public. Policy changes, maybe limiting groundwater extraction to maintain lake levels in lakes that are prone to lower lake levels, incentivization policies to reduce kind of water use and encourage water infiltration, conservation practices, like I talked about before, wetland restoration can help kind of moderate lake levels, putting in lake habitat for fish species that can be resilient to changing lake levels, and engineering, maybe management, water level management with some dams. Lakes that have dams on them needs to be thought about, designing infrastructure that can accommodate extreme events, perhaps something like rolling or floating piers, so that folks on the lake can kind of easily adjust to lake levels. Next slide. So we're just going to go through these quick. I'm not going to talk about all of them, but we have adaptation actions for water quality. Next slide. AIS, next slide, and fisheries, next slide. So I just wanted to kind of show those to you. I didn't expect you to read all of them. If you want more information, feel free to give me a call or an email. But all of those adaptation actions kind of fall into these 4 categories that we talked about before. They additionally kind of represent a resistance, resilience, or response approach. And then all of the strategies that we developed both meet the need of the lake ecosystem, so they will work within kind of the function of the lake, but they're also reasonable to consider with the human dimension. Not every particular action may work in every situation, but we tried to consider both of these in kind of pulling together a list that folks would have available. So next slide. So resources, we put together a publication about all of this, talking more in depth about specific adaptation or specific climate changes kind of in those 4 themes, and then also adaptation strategies for lakes in Wisconsin. And then we also put together this document shown on the right called Climate Wisconsin 2050 for lakes. And Pat has it. I don't know if maybe he could pull it up right now to kind of show you, but it's also included where you clicked on the Zoom link. There's also a handout link below that, so you guys can have this Climate 2050 document available for you. If Pat is trying to show it, I can't see it on my screen. But this document kind of shows or talks about within kind of the 4 categories. Oh, thanks, Pat, that we covered in the paper. If you want to just kind of scroll through so people can look at it just briefly here. We talk about expected air temperature and precipitation changes by, the year 2050. So this is kind of what we expect in 2050. And then gives a little overview of kind of the adaptation framework that we talked about, this resistance, resilience, and response approach. And then for each of those areas, specific climate impacts, and then also adaptation strategies. So this is a document that you guys are welcome to all have, print off, use however you would like, share with anyone, and use it, in any way that you see fit to help with, possible either understanding climate changes for Wisconsin lakes, or thinking about maybe what you could do on a local level for any particular lake that you're interested in. So with that, it's kind of the end of my presentation, and I think we have a little bit of time for questions. I will say, if we don't get, if everyone doesn't have a chance to ask their question, or I don't have a chance to answer, feel free to email me. I'm going to put my email in the chat box, so you guys have it in case you have any follow-up questions.
Madeline, maybe you could put the link to this document in there too, just so people can find it easily, please.
Yes, I can do that.
Thank you.
Wow, lots of, oh, we got a question from Tom. Let's just bring that back up. So Tom's asking, what other fish species besides largemouth bass do you expect to thrive during the warmer temps?
Yeah, that's a great question. So I'm not a fish expert. I know a lot about cold water fish. I know a lot about Cisco, which is why I put it in my presentation. But more or less, you can expect any kind of warm water fish species to thrive in the future. So these species are actually going to have an advantage for two reasons. One reason is that, water temperatures are going to be warmer, and they are more adapted to warmer water temperatures. The second is that in a lot of lakes, not necessarily on the southern part of our state, more so in northern Wisconsin, these kind of warmer adapted fish species actually need, warmer temperatures, obviously, but also more dissolved oxygen in the water generally than cooler fish species do. So what we find is that in many lakes, so I think, lakes in far northern Wisconsin, northern Minnesota, Canada, they have fewer warm water fish species, not necessarily because the water doesn't get warm enough in the summer, but because those fish species actually die off in the winter. So you'll have winter kills under the ice because they don't get enough dissolved oxygen. So because we have less ice cover, that's less of an issue. So they kind of get an advantage in two ways. The temperatures are warmer, and they don't have to worry quite as much as fish actually can worry about fish kills in the winter. So the short answer is basically any warm water fish species will have an advantage moving forward.
All right, thank you. Somebody was asking for the graphs in your presentation and how we can get them. And Gina Liberty from DNR posted a link there. So
Yep.
if anybody else is interested, click on that link and you'll be able to find them.
Yeah, so all of the climate projections were from Wiki, and Gina shared the link in the chat box. Thanks, Gina. If you have any questions about the graphs of anything else, feel free to send me an email, and I can direct you to either the publication that it's in, or share the graph with you if it's one of my own graphs.
Great. Well, not seeing really any other questions coming through. Madeline, did you want to put up your email on there so people can know where to contact you?
Yeah, so I put my email in the chat.
Okay.
Yep, you might have to scroll up a little bit. It's in there, but it's just
yep.
madeline.magee@wisconsin.gov. So it's in there if you scroll up in the chat a little bit. And I also put the link to the handout